Welcome to AI Frontiers, your gateway to tomorrow's intelligence. Today we're exploring 13 breakthrough papers from artificial intelligence research, published on July 25, 2025. These cutting-edge studies showcase the remarkable convergence of theory and practical applications, spanning from hierarchical learning systems to biologically inspired approaches that mirror human cognition. Join us as we journey through the latest innovations that are reshaping the boundaries of what intelligent systems can achieve. Our exploration today follows a structured path through AI innovation. We'll begin by examining 6 dominant themes that characterize current artificial intelligence research, each representing critical areas where significant progress is being made. Then we'll discover breakthrough findings that challenge conventional wisdom and open entirely new possibilities. We'll examine sophisticated methodologies from leading researchers, highlighting their strengths and limitations. Finally, we'll dive deep into 3 seminal papers that define the field's direction and chart the future landscape of artificial intelligence. The computer science artificial intelligence field, commonly known as CS. AI, represents the architectural blueprint for intelligence itself. This core domain encompasses everything from intelligent agents and machine learning algorithms to reasoning systems and autonomous decision-making processes. It serves as the invisible infrastructure powering our intelligent world. Every smartphone query, autonomous vehicle navigation, and medical diagnosis system rests on foundations laid by CS. AI research. This field tackles the fundamental questions of how machines can learn, reason, and make decisions, constantly evolving to push the boundaries of what machine capabilities can achieve. Think of CS. AI as the computational heart where researchers design the very essence of artificial intelligence. The first major theme in current AI research focuses on hierarchical and multi-level learning systems. This approach recognizes that complex problems often require decomposition into manageable sub-problems, with different levels of abstraction handling different aspects of the overall challenge. Like a master chef working simultaneously at meal planning and specific cooking technique levels, these systems operate across multiple scales. Fard and colleagues demonstrate this through hierarchical reinforcement learning for asset management, where budget allocation decisions are elegantly separated from maintenance prioritization tasks. Similarly, neuro-symbolic term rewriting systems show how symbolic reasoning can be integrated with neural learning at different hierarchical levels, creating systems that both learn patterns and apply logical rules systematically. Resource-constrained and efficient AI systems represent our second major theme, addressing the growing need for AI deployment in resource-limited environments. As AI models become increasingly complex and computationally demanding, researchers are developing innovative approaches to maintain performance while dramatically reducing resource requirements. The knowledge grafting mechanism exemplifies this trend, achieving a remarkable 88% reduction in model size while actually improving performance. This is like the difference between a gas-guzzling luxury car and a hybrid vehicle delivering the same performance with a fraction of fuel consumption. These advances are critical for edge computing, mobile applications, and democratizing AI access across diverse computing contexts where every computation cycle matters. Multi-modal fusion approaches constitute our third theme, recognizing that real-world AI systems must integrate information from multiple sources. The PhysDrive dataset exemplifies this by combining RGB cameras, near-infrared imaging, and millimeter-wave radar data for physiological monitoring. Our fourth theme focuses on uncertainty modeling and partial observability. Wang and colleagues successfully trained humanoid robots with incomplete state information, while constraint-based belief states handle imperfect information scenarios. Finally, biologically inspired AI emerges as our sixth theme, drawing insights from neuroscience. Dual-process models mirror hippocampus prefrontal cortex interactions, recognizing that millions of years of evolution have solved many problems AI researchers tackle today. Several paradigm-shifting breakthroughs from these papers represent significant advances that could fundamentally reshape AI system design. The first major finding involves successful training of humanoid robots under partial observability. For the first time, researchers demonstrated stable learning using only 1/3 to 2/3 of original state information. The second breakthrough shows dramatic efficiency gains through knowledge grafting. achieving 88% model size reduction while simultaneously improving generalization capability to 89.97% validation accuracy. The Pareto NRPA algorithm demonstrates superior performance compared to evolutionary algorithms in constrained spaces. Neural systems now match GPT-4o performance on reasoning benchmarks, while the OS-MAP benchmark provides comprehensive evaluation frameworks that could accelerate progress across the entire field of computer-using agents. Current AI research employs several sophisticated methodological approaches, each with distinct strengths and limitations. Hierarchical reinforcement learning handles exponentially large action spaces by structurally separating different types of decisions, though it requires careful design of hierarchical structures. Neuro-symbolic integration combines pattern recognition capabilities with logical reasoning power, offering the best of both worlds but requiring deep understanding of different computational paradigms. Multi-modal sensor fusion provides robustness against individual sensor failures while capturing complementary information, though it increases data processing complexity. Constraint-based reasoning offers mathematical rigor for handling uncertainty, while Monte Carlo extensions balance exploration and exploitation across multiple objectives, though computational costs can become prohibitive for large search spaces. Fard and colleagues tackle one of the most challenging real-world AI applications through hierarchical deep reinforcement learning for multi-year asset management. Their work addresses infrastructure management that combines long-term planning, resource allocation, and uncertainty management under strict budget constraints. Imagine maintaining an entire city's water system with limited budgets and uncertain failure rates. The core innovation decomposes the problem into two hierarchical levels: a high-level budget planner operating annually for strategic budget allocation, and a low-level maintenance planner making tactical decisions within allocated constraints. The methodology integrates linear programming projection within a hierarchical soft actor-critic framework, ensuring rigorous budget compliance while maintaining deep reinforcement learning flexibility. Experimental evaluation on sewer network management demonstrates superior scalability and convergence, providing a template for transportation networks and power grids. Petruccellis and colleagues address the fundamental challenge of building neural systems capable of learning and executing symbolic algorithms through neuro-symbolic convergent term rewriting systems. This work sits at the intersection of machine learning and symbolic reasoning, tackling whether neural networks can truly master symbolic computation. They introduce two complementary architectures: the neural rewriting system and fast neural rewriting system, both inspired by rewriting algorithms themselves. The key insight is that neural networks can learn symbolic operations if structured to mirror underlying algorithmic processes. Rather than treating symbolic reasoning as emergent from large-scale computation, they explicitly design architectures reflecting systematic term rewriting nature. Experimental evaluation shows both systems significantly outperforming neural baselines and matching OpenAI's O1 preview model on reasoning benchmarks, suggesting architectures designed for symbolic reasoning may offer advantages over general-purpose language models. Wang and colleagues achieve a significant breakthrough in humanoid reinforcement learning under partial observation, demonstrating the first successful training with incomplete state information in the challenging gymnasium humanoid V4 environment. Humanoid locomotion requires precise coordination of numerous degrees of freedom while maintaining balance and forward progress, all with incomplete information, like learning to walk while blindfolded with limited feeling. The environment demands coordinating 17 degrees of freedom while maintaining dynamic balance and responding to perturbations. The key innovation involves a novel history encoder processing fixed-length sequences of past observations in parallel, avoiding computational and training challenges of sequential processing. Results show learned policies achieve performance comparable to full-state access despite using only 1/3 to 2/3 of original information, suggesting much typical state information may be redundant for effective policy learning. These breakthroughs point toward fascinating future research directions as AI development enters a new phase where methodological boundaries become increasingly fluid. Integration of hierarchical learning with multimodal sensing and uncertainty modeling could lead to autonomous systems capable of long-term planning and adaptation in complex, dynamic environments, From vehicles navigating years of changing traffic patterns to robotic assistants adapting to evolving household routines. Neuro-symbolic approaches suggest broader trends toward hybrid architectures combining neural learning with symbolic reasoning, potentially enabling sophisticated mathematical reasoning and scientific discovery while maintaining neural network flexibility. Knowledge grafting efficiency gains point toward democratizing advanced AI technologies, enabling sophisticated applications in developing regions, remote locations, and mobile contexts where computational resources are limited through systematic resource-constrained deployment approaches. This synthesis was created using GPT and Anthropic Claude Sonnet 4-202514 for comprehensive analysis and content generation. Text-to-speech synthesis is powered by Google text-to-speech technology, ensuring clear and natural audio delivery. Image generation utilizes Grok AI visualization tools to create compelling visual representations of complex AI concepts. All content has been reviewed by human experts for accuracy and clarity, though we acknowledge that some oversights may exist despite thorough review. Our commitment to transparency ensures you understand the collaborative process between artificial intelligence tools and human expertise that brings you these insights into cutting-edge research developments. Subscribe to our YouTube channel for cutting-edge AI insights and weekly deep dives into the latest artificial intelligence research. We provide expert analysis of breakthrough papers and methodologies, making complex research accessible to developers, researchers, and tech enthusiasts alike. AI Frontiers serves as your gateway to tomorrow's intelligence, keeping you informed about the rapidly evolving landscape of artificial intelligence. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.